In this class, we are going to prove that center of an element is a subgroup of G. Now the question is, what exactly center of element is? So the definition says, given a group G, obviously given a fixed element of G, we are calling it as A. So center of that element is defined as center of A is equal to collection of all those elements of G that commutes with A. Now we have to show that this is actually a subgroup of G. So in order to prove it, we will take the help of one step test again. So what does it say? Given a group G, given a set H, if we have to show this H is a subgroup of G, we are supposed to show H is non-empty, H is a subset of G, because this is the assumption of one step test, and after that H will be a subgroup of G if the condition is satisfied. That is, AB belongs to H implies AB inverse belongs to H. Now the first step comes to show C of A is non-empty. Now why it will be non-empty? Our simple observation is that G contains one element, at least one element, which is going to commute with A. That is always going to happen. In fact, there are two. Which are they? So note that what will be EA? EA will be always A, right? And what will be AE? AE is also going to be A. It means the identity element E commutes with A, and therefore it lies in center of an element. There is one more element, which A, because A into A is going to be A square. Thus A also commutes with itself. That is always going to happen. So that element can also be used to show C of A is non-empty. But here we will say E always commutes with any element of the group. In fact, in this case, E commutes with A, therefore E belongs to center of A, and therefore center of A is non-empty. No issues for subset, because center of A is actually collection from elements of G itself. So clearly we will say center of A is a subset of G. Now, in order to go for the subgroup test, we should take two arbitrary elements from C of A. So we will say let us call that elements as some G1 and G2. So we will say let G1 comma G2 belongs to C of A be any elements. But what do we know? Center of A contains those elements that commutes with A. Therefore, what will happen? This G1 and G2 both will commute with A. Now, in order to proceed ahead, we need something extra here. As we have to show G1, G2 inverse belongs to center of A, isn't it? Because we have started with two arbitrary elements, G1 and G2. Since that G2 inverse is in picture, I have to convert this G2A is equal to AG2 in terms of G2 inverse. So how we can do it? We will simply pre and post multiply by G2 inverse to this equation here. So I will say pre and post multiply by G2 inverse. So what we will get? This will imply G2 inverse G2A G2 inverse will be G2 inverse A G2 and G2 inverse, which further implies, as we know, G2 inverse into G2 will be identity element, so this will be vanished out. So we will simply have A into G2 inverse on the left hand side. Similarly, on the right hand side, we will simply have G2 inverse A. So I will call this G1A is equal to AG1 as 1 and let us call it as 2. Now, as we have to show G2 inverse lies in C of A. So in order to show it, what we have to show? As we know, center of A contains elements that commutes with A. So we are supposed to show that this G1 G2 inverse commutes with A. So what I will say? We have to show now this G1 G2 inverse commutes with A. So we'll simply consider the left hand side and we will move towards right hand side. So I'll say consider G1 G2 inverse A. Now using the associative property in groups, so this is equal to G1 G2 inverse A, which is further equal to, from 2 what do we have is G2 inverse A is actually nothing but A G2 inverse. So this is same as G1 A G2 inverse, which is further equal to, again use the associative property. So this is actually equal to G1A G2 inverse, which is further equal to, now from 1 we do have value of G1A as well. So this is AG1 G2 inverse. So this is using 1 and this was using 2, which is further equal to, again use associative property, A G1 G2 inverse. Therefore what we have shown is this G1 G2 inverse commutes with A, right? And therefore this G1 G2 inverse is a member of C of A, and therefore this C of A is actually a subgroup of G, and that is exactly what we wanted to prove.